Welcome, ladies and gentlemen, to this webinar on X-ray topography. My name is Martin Ferenc. I'm Business Development Manager of Rigaku Europe, and I have the pleasure to moderate this webinar, which is basically a collaboration between Rigaku and Fraunhofer ESB Institute for Devices and Integrated Circuits. We will spend some time today to give you some insight in the topic of X-ray topography. We all know X-rays. We know the principles of X-ray tomography, like using the X-rays to make some images of things in sites. And we also know the phenomenon of diffraction. Diffraction is basically the phenomenon which happens when an X-ray gets scattered on a periodicity within matter. X-ray topography is basically the combination of these two technologies. So it gives us an imaging, we get images of diffracted beam intensities. And in this case here from semiconductor material. It can be used to investigate and understand defect structures and different type of defects in semiconductor material. So we will have three parts in this webinar. The first part is from my colleague Takayuki Konga. He will give us a basic introduction into the technology and the system which is used. And in the second part, Mr. Roland Weingärtner from Fraunhofer Institute will show us a couple of examples of real-life examples, what the system can do for the different materials. And the third part, hopefully we have some minutes at the end of the presentations to answer your questions. If you want to raise a question, please do not use the chatter function because that might be deleted at the end. Please use the question and answer button on the bottom. So then your question will be stored, and in case we will not have time to answer it during the session, we will come back to you later on. Okay, so enough from my side. So I would like to hand over to Taka to start with his part of the presentation.
Thank you. So I will open my presentation file. So wait a moment. Hello everyone, I am Takayuki Konya from Rigaku Europe SE. Initially, I would like to explain our advanced X-ray topography imaging system, XRTmicron. At my part, I explain some basics of X-ray topography and introduce our technology. In the literature, the definition of X-ray topography is that X-ray topography is the generic name for a family of X-ray diffraction imaging techniques capable of providing information on the character and distribution of crystallographic defects in large, nearly perfect single crystal materials. Nowadays, the X-ray topography technique is one of the most important methods for understanding single crystal substrates. This technique uses the X-ray diffraction for imaging inside of the materials. As well known, X-ray was discovered by Röntgen in 1894. X-rays are a form of the electromagnetic radiation with wavelengths of 0.01 to 100 angstrom. Crystal is characterized with the periodic arrangement of atoms, ions, or molecules in the 3 dimensions. X-ray diffraction is a technique of observing crystal structure information. It occurs when X-ray exposure to crystal and the Black's law falls. X-ray topography uses these methods to observe imaging data. This picture shows you about principle of X-ray topography. If X-ray has exposure to single crystal sample like silicon wafer, X-ray diffraction will occur as Black's law. If the sample has defects in the crystals, we can detect the crystal defects as image with 2D detector. The image includes deformations, dislocation, and so on. This is one example of X-ray topography. If sample has grain boundary, we can obtain the information of grain boundary image. There are lattice planes and grain boundaries. X-ray has exposure from X-ray source and optics. The diffracted beam are obtained at 2D detector, and we can see the 2D image. From these results, we can understand that each grain has another size and crystal diameter. This slide shows the results of calcium fluoride single crystal wafer and magnesium oxide single crystal wafer. You can see the grain boundary image of calcium fluoride and magnesium oxide. X-ray topography technique enables to see the grain boundary information. Also, X-ray topography can visualize information of defects like dislocations. There are lattice planes and defects inside of sample. X-ray has exposure from X-ray source and diffracted beam is detected at 2D detector. We can get defects information from the image. This is one example of X-ray topography image of SiC single crystal wafer. We can see three kinds of dislocations inside of wafer. One is TSD. TSD is threading screw dislocations. This is shown as strong dot-like shape in image. TED is threading edge dislocations. This is shown as a weak dot-like or short line shape. BPD is basal plane dislocations. This is shown as weak long line. XRTmicron has 3D imaging function of dislocations, which calls section topography. In a section topography, the depth direction distribution of lattice defects within the sample crystal can be determined. The system measures section topography with shifting the sample positions of small interval less than beam width. The visualization of three-dimensional or equal depth defects images can be achieved by using certain image processing software. After measurement of section topography, we can make this kind of 3D image. Also, we can see the slice image of selected depths. This is a photograph of XRTmicron system. This system can connect with all sample loader units. This one is topograph system main unit, and this one is autoloader unit. XRTmicron has these kinds of unique features. X-ray source, we use micro-focus high brilliance rotating anode. For incident optics, we use multi-layer parallel beam collimator. Also, crystalline collimator can be used and auto sample changer is available. Colorimeter system for both transmission and reflection geometry capture digital image with high sensitivity and high resolution X-ray camera. Dislocation analysis by topography image. The red colored lines are Rigaku original technology. We can offer XRTmicrons as not only for R&D, but also for quality control. From next slide, I would like to explain these features in detail. These pictures show you the two key components of XRTmicron. One is X-ray generator, second one is X-ray mirror. We use the rotating anode type X-ray generator named Micromax 007HF for X-ray source. This is high brilliance rotating anode point focusing X-ray source. The maximum power is 1.2 kilowatts. Effective focusing size is 0.07 mm. Effective power density is 310 kilowatt per millimeter square. This X-ray source is used with high precision X-ray mirror to make collimated beam. These pictures are detectors for XRTmicron. We have two types of detectors. The difference between two cameras are pixel size and resolution. These cameras are manufactured by RITE, Rigaku Innovative Technologies Europe. The pixel size of high-sensitive camera is 5.4 micron, and that of high-resolution camera is 2.4 micron. We can select these cameras to use its XRTmicron system. This picture shows inside of XRTmicron. On the right side, this is incidence site. There are X-ray source, multi-layer mirror, and crystal collimator on source arm. On the left side, there are scintillator counter and X-ray camera. Sample is mounted on horizontal sample stage. This goniometer enables easy exchange between transmission and reflection topography geometry. Also, crystal collimator can be employed for high sensitive measurements. This is a schematic view of the XRTmicron. In the reflection method, the X-ray source is upper side of the sample. On the other hand, the X-ray source is under the sample stage in the transmission mode. This X-ray generator has dual wavelength function, so we can change the wavelengths of copper and moly from software. This slide shows you the measurement positions of various measurements. The copper and moly radiation are used in XRTmicron. The copper source is mainly used in reflection mode. Copper source can use with crystal collimator. In the case of locking curve measurement, scintillator counter is used. Locking curve measurement is also used for curvature correction. The moly source is mainly used for transmission geometry. In the case of section topography, section slit is used with moly source. In the measurement, we can use two methods. One is snapshot mode, the other is TDI mode. TDI is time delay integration measurement. Sample is traversed with X-ray exposure in TDI measurement. Total measurement by snapshot imaging requires tremendous amount of time, and TDI measurement can use with shorter time than that of snapshot measurement. If we want to get full information of total wafer, the image is made with merged several TI measurements. In this example, 4-inch pattern wafer of silicon was detected with TDI measurements. XRTmicron can be used with odd sample loader. This picture shows you inside of sample loader. This is multi-row cassette. It enables to put 3 to 12-inch wafers. If we use XRTmicron with wafer loader, XRTmicron can be used for quality control. This is a picture of control software. This software has measurement macros. Customer can make their own sequence macros. In this example, automation macro from sample loading, alignment, locking curve, topography imaging, and sample eject is set. This is end of my slides. Thank you for your attention. Now I change the presenter to Dr. Weingartner. Thank you. So now I change to I stop the sharing. So Laurent, so please open your presentation.
Okay, thank you very much. So now you should see my presentation. Also, I would like to welcome everybody to our first X-ray topography online seminar in 2020. My name is Roland Weingartner and I'm from Fraunhofer Institute for Integrated Systems and Device Technology, ISB, located in the city of Erlangen in Germany.
Roland, please check if your slides are on, because I can't see them.
Ah, you can't see? Oh, sorry. Maybe now you can see it.
Now you are there. Yes.
Ah, okay.
You.
I'm sorry. My mistake. Okay, great. Okay, so I will continue with this second sheet. So we at Fraunhofer Institute founded together with Rigaku in the framework of a strategic cooperation, the Center of Expertise for Topography. So we serve as a test laboratory for our clients. So the idea is that the clients come to us with some certain measurement problem, with some certain measurement task, and together with the client, we will find solutions. So in this sense, we give scientific assistance to the client. Let me please emphasize some, let's say, major properties, important properties of the XRTmicron, which in my opinion are maybe the most important one. So it is a laboratory scale instrument. Yeah, and such, yeah, you have, let's say, can make quick measurements, you have a large throughput, and as a laboratory scale instrument, we have 100% accessibility. And in this sense, yeah, you have actually, it's superior to a synchrotron in terms of handling, and this also at moderate costs. And it is very important to note that we have here a non-destructive structure characterization tool, yeah, with really high quality in quantitative defect characterization of complete wafers you may use in research and development. So therefore, the clients typically are, for instance, wafer suppliers, yeah, or device suppliers, which may use the equipment for quality control. Yeah, the wafer suppliers are interested, for instance, in improvement for the growth process, and also to have performance control feedback to the growth process. And they may also provide a specification sheet to the client. Also, the device suppliers use it as an incoming control tool, yeah, to see how good the substrates actually are. And they can also control, yeah, the epi-layer processes on the substrates, yeah, and detect and to see how these defects propagate in the epi-layer and how they may affect the devices. And this is actually, I would say, my major task of this second part of my talk. I will show you, yeah, that this tool is actually useful, yeah, for instance, for these wafer suppliers or device suppliers. So therefore, I will proceed as follows. First, I want to talk about general performance of the XRTmicron, especially with respect to which materials can be used, which kind of defects we may see, and also I will address resolution and penetration into the material. Then I will go to concrete examples, for instance, bulk materials. Here I want to pick actually some, from my opinion, very important example, the quantification of reading screw dislocation in 4H silicon carbide. And another example I would like to show is application on bulk nitrides like aluminum nitride or gallium nitride. The next big topic is the epilayers. So here I will show you applications on heteroepitaxy, for instance, how we can characterize gallium nitride on sapphire. Another example I would like to address is the homoepitaxy. So it means 4H silicon carbide layer on 4H silicon carbide substrate. Finally, I will show you also three-dimensional reconstruction, so this 3D imaging, which Taka has already presented. I will show you more examples with respect, for instance, to silicon, glide planes in silicon, wafer, and also I come back to the topic of homoepitaxy, and here I will show you how defects are formed inside the epilayer, for instance, the skilling defect, triangle defects in 4H silicon carbide. Okay, so let's start with some general performance, and here the first question which arises is what can we actually see? Taka already mentioned that about measuring of grains. Yeah, so here you see also a concrete example. We have aluminum nitride wafer. So as also Martin in the beginning mentioned, it's actually diffraction tool. It means where you have a dark color, it's a high intensity, and where you have no diffraction. Yeah, so it means you have no signal, so it's white here. Yeah, it's low intensity. It means in this case that we see here grains. So you can easily detect if something is out of the diffraction plane, if you have, for instance, here grains. Nevertheless, I would say most important applications is also detecting of line defects. Yeah, here in an example 4H silicon carbide, what you see here in the background is a transmission measurement of the 1-101 diffraction plane. And you can see here now very crowded, a lot of black structures, which are actually line defects and planar defects and dislocation clusters. I will come to this later on, but here you have a first impression how such a thing looks like. Then also what we can detect is deposited structures. Yeah? So if you have a processed silicon wafer with some devices, with some structures on it, we see these structures, and even more, we see below also inside the silicon wafer, for instance, defects. Yeah, here you see, for instance, glide planes, which are penetrating here inside this deposited structure. So here you can imagine that this would be very useful to predict where you may have a failure in your device. Also, let me mention finally that we can also detect wafer damages. Because for some materials, for instance, aluminum nitride, it's still a hot topic, how to make the mechanical finishing, the polishing, and so on. And also the XRTmicron can be used actually to see induced defects by mechanical finishing, which you here, for instance, is saw marks. Of course, not everything can be measured. So please note that point defects or very small voids and volume defects is not observable actually. Okay, so what materials can be mapped? Well, the answer is very optimistic. We can measure almost any crystal. Yeah, so and what depends this almost, of course, on the accessibility of reflexes of a diffraction plane. And this depends also, for instance, on the goniometer of your equipment. And here in the XRTmicron, as already Taka mentioned, we have really a very large range in the goniometer arms, in the source and detector range, that we can have reflection, transmission measurement, and therefore a lot of reflexes are actually accessible. So therefore, and we can measure wafers from 300 millimeter down to 1 inch or even less. So here you see, for instance, silicon, yeah, a 300 millimeter wafer. Then you see a sapphire substrate. Here is an example for H silicon carbide, gallium nitride substrate, and here a 1 inch aluminum nitride substrate. Of course, these are examples I will show in more detail now in this talk. Yeah, of course, there are much more materials which you may are interested in. You could measure. For instance, we measured also gallium arsenide, germanium, indium phosphide, cadmium telluride, and so on. So there are, of course, no limits of the materials you are interested in. But here in this talk, I will mostly rely especially on this wide bandgap materials here. Okay, so what do I mean with complete mappings? So please note here, this is a 100 millimeter 4H silicon carbide wafer and in transmission measurement. And now the complete mapping means that the topograph, we can also make a zoom and use the full potential of our resolution of the CCD camera. So I can zoom in at any position, enlarge it, yeah, enlarge it further, yeah, and even identify individual dislocations, yeah, enlarge this further until I reach really the resolution limit of about 5 cross 5 square micrometers, which corresponds to the resolution of our CCD. Of course, we can go with the high resolution camera even more down to 2.4 micrometers, if you have seen in the talk before. Okay, but let me emphasize that this is one measurement, which will take maybe 1 hour or something like that, yeah, in this magnitude of order. And you have, after this measurement, you can zoom in at any position. Yeah, of course, these files are very large, more than 1 gigabyte, yeah, but you have the complete information available after this measurement at any position of your wafer. So this is very powerful tool, yeah, to have characterize actually fully your wafer. Okay, so here I would like to show you that we are actually competitive with a lot of applications with the synchrotron. Here is an example again, silicon carbide. On the left-hand side, you see now a reflection measurement, asymmetric reflection measurement, the 1,1-28 reflex done by a synchrotron. Yeah, and here marked with these red areas, yeah, you see it can identify now some defects. And on the right hand side, yeah, we may measure the same position now with the XRTmicron. One with reflection and the other one here in transmission. And what you can see that actually also all these defects are marked, and we have actually exactly at the same positions, yeah, we have exactly the same structure of defects as it should be actually. Yeah? So therefore you see we can exactly, let's say, identify the defects like in a synchrotron. There is no drawback. Yeah, so there is no need to go to a synchrotron if you want to map your wafer down to that you can identify actually your dislocations. And even more, we can change very rapidly, yeah, from reflection to transmission. You do not need to change your sample, and you can measure now the transmission measurement and so on. And with this combined information, you can, let's say, have a lot of additional information about your defect structure. So let me address shortly also the effect of attenuation. Yeah, this is also a very important topic if we want to measure reflection, transmission, also in combination with epilayers. So we need to know something about penetration. So as Stucker has already mentioned, we have 2 anodes, molybdenium. Yeah, it's about 0.7 angstrom, and the double almost 1.5. And something is our copper anode. And so the wavelength is double. Nevertheless, the attenuation coefficient, yeah, it's about 10 times higher. So what you can see is attenuation coefficient versus energy. Now for 3 examples here, namely low density materials, electron density materials like silicon carbide and aluminum nitride, and also a high electron density material like gallium nitride. And so please note that the difference here is a factor 10 in the attenuation coefficient between these 2 different anodes. These rotating anodes we have in the XRTmicron can be also changed programmatically very easily. Nevertheless, in gallium nitride, since to this absorption edge, yeah, so this is in this sense a complicated material, yeah, we have no difference between these 2 anodes. This you can also see now at this sheet. Please look at the last row. There we have penetration depths, yeah, which depends, of course, of the attenuation coefficient. For this material, silicon carbide, aluminum nitride, here we have almost in the same order. The penetration depth for copper, it's about 70 micrometers. And for molybdenum, it's about 500 micrometers. So it's clear that for molybdenum, it's easy to penetrate a complete wafer, which is about 350 micrometers. On the other hand, yeah, it's important for reflection to have a low penetration, because especially in your epi-layer, you are interested in information out of your epi-layer. This we see later on in a concrete example. Note that in gallium nitride, for instance, you can almost measure only good in reflection, since due to the low penetration depth. Okay, so now sufficient for general performance at the moment. I will apply this and show this now on concrete materials and also concrete, let's say, measurement tasks. So for the bulk materials, I would like to discuss now the quantification of reading screw dislocations in 4H silicon carbide as a concrete example. Okay, first of all, if I want to measure reading screw dislocation, I have to decide what kind of reflex should be chosen. Now here I have made a measurement of silicon carbide with the 008 reflex and with the 1,1-28 reflex, the same position. And what you can see, some reflexes here are seen in either topogram, and other reflexes, for instance, the green circles you see here in the 008 diagram, nothing, whereas you can see very well, not so pronounced, but you still can see this. You have here also defects, and here you have here some line-shaped defects here. And this is now important to identify. There it's well known that GP criterion, which helps you here. It means what you have to look for is that dislocations, reflexes which bend the lattice plane or which bend not the lattice plane. This you can estimate with the GP criteria. Where it is 0, it means that you cannot see respective dislocation. Yeah, so it means now, for instance, for the 008, you do not see 3D X dislocations in the basal plane dislocations, either of screw or edge type. Only you have 3D screw dislocation. And this is exactly now how you can exclude, yeah, that these defects, yeah, cannot be 3D X dislocations, so they have to be 3D screw dislocations. So therefore, our conclusion is, if we want to map 3D screw dislocations, it's sufficient to measure the 008, let's say, topograph, and make dark spot counting. This is exactly now the method. We measure this topogram graph, and then, of course, we have to now to make some dark spot counting. So we make background correction in order to are able to set a meaningful threshold, and we can now count our dislocation. And then doing so, you have here now a concrete example, yeah, of such a 4H silicon carbide wafer. You can make now these colors with respect to the density, yeah. And also you can calculate mean density here. This is now below 1,000, for instance, or you can make statistics, a radial distribution, or also to see how your density is distributed over the wafer. Okay, I want just make some small comments on the reliability of this method. Of course, it depends on defect recognition, yeah, which you can see here. So you can automatize that these defects are recognized. Not only the position is important, also the shape is somehow important in order to be sure that there's no overlap. Yeah, so if you have overlaps, the circles are larger. So you can, with eccentricity and with the semi-major and minor axis, it should be have a small Gaussian shape. Then you are sure that your detection is good. And also, I would like to show you some limits. This is an example of, let's say, a very high density in silicon carbide. So here you see in the middle that it's very crowded. The dislocations, they start to overlap. These are by densities well above 3,500 per square centimeter. So this is a kind of upper limit, actually, of our method. Nevertheless, this is a very high value for 4H silicon carbide, because usually, if you see here such a density map, the defect density is very well below this 3,500, so that we do not have the problem in commercially available wafers to detect actually this 3D screw dislocation, which you can see here in this original topogram of the 008 wafer. Here enlargement, you see that all these points, it's easily, let's say, they are well separated, so you can easily detect this, count these reading screw dislocations. Similar processes can be done also on the 1-1 asymmetric reflex in order to count the lines, in order to have also a basal plane dislocation density. But of course, detecting lines is much more complicated, it is much more sophisticated. Here I will not go into this topic in this talk. So let me, more important in my opinion is also the big advantage you have, because usually if you want to process now an epi-layer whatsoever, you want to have information about this defect distribution. And usually what the people are doing, for instance, the crystal growers, they need to make KOH etching of the wafer, and here it's a destructive method. But our method is non-destructive. And it's also relatively rapid and can be done for all of your wafers if you like. No? And therefore you do not destroy wafers, and you can save, let's say, also a lot of money per pool because you can sell the wafers. Okay, this should be sufficient now for 3D screw dislocations at this moment. I will come to this back a little bit later when I talk about this homoepitaxy of 4H silicon carbide. But now I would like to continue to the nitrides, especially aluminum nitride and gallium nitride. First, to gallium nitride, what you see here is a freestanding gallium nitride wafer, 2-inch substrate, measured with an asymmetric reflex 1,1 minus to 4. And you see here this somehow noisy image in the first side, but you can zoom in, and you see also kind of clusters. This is somehow surprising because that high dislocation density in gallium nitride is very well known that it's very high. Yes, it's 10 to 7. So please remember 3,500 for silicon carbide, is a limit. So here you are well above limit. Everything is overlapping actually. Nevertheless, these defects are, let's say, are crowded, they cluster, and you can see these cluster structures, which itself is also now important if you want to make, for instance, a further processing of your wafer. This can be also shown and proven with cathodoluminescence. Here also we see that the defects, actually here we can resolve the defects and can see that you have here some clustering. But of course, such an image, it's very complicated in cathodoluminescence in the scanning electron microscope to achieve this actually, and you have no chance to make a complete wafer, not at all. Okay, so let's continue to aluminum nitride. Here I would like to mention that in our institute, we have a lot of groups here, in Fraunhofer, and one group is also growing aluminum nitride bulk crystals. This is now a very interesting topic for power electronic devices. It's a wide bandgap semiconductor. And we grow this in our in-house. And of course, we use the XRTmicron tool also for characterization. Yeah, so here you see a typical example of such early results of our crystals. So you can here actually see it's a nice example in the sense that you see all kind of defects, for instance, misoriented grains. Here, this is also very important because for growth reasons, you have to fix the crystal somehow, and this is exactly where these grains form. And that's unavoidable somehow, but it's important where they are, how they evolve, and how they, let's say, have limits our diameter enlargement, for instance. So this is a very important to have feedback for the crystal growers. Yeah. And despite of these grains, of course, you see defect clusters. You have also large regions almost free of defects. And this defect propagation can be, let's say, monitored very nicely, yeah, very quick. And you do not need to go to the synchrotron, because for crystal growers, it's important to have quick feedback. Yeah, in order that he can, in some days, make the next measurement and the next growth and so on. Yeah, so this is very, very important to have such a tool available for crystal growth. Okay, here I would like to show you some application of Berger's vector analysis. As I do not want to go too deep inside this topic, just some basics, which is here very easily seen on these 4 topograms. So this is the same, so it's 4 topograms at the same position. The 0, 0 in the A topogram, you see the 0, 0, 4. Symmetric reflection. At the center, you have here a very nasty dislocation cluster. And in the surroundings, you see, for instance, that you have no 3D screw dislocations, or almost no 3D screw dislocations. Then, if you now, so this G vector is perpendicular, yeah, to the to our image. And now, if we go in plane, yeah, in the basal plane, the G vector. So choosing the G vector like this, we see now, yeah, that the basal plane dislocation pop up. Yeah, and this is now very interesting. We can now change the direction, always keep inside the plane, but change it with 60 degrees always. Yeah, and you see always if the G vector is perpendicular now to the Berger's vector, we cannot see the basal planes. No? So the red basal planes here in this side, so this vertical is not seen, but it's seen here. Yeah, but here the other ones, this red here, perpendicular to the G vector is not seen. So this is of course expected due to the GP criteria. So in this sense, you can analyze, yeah, Berger's vector of this basal plane dislocations. So if you want to have more information, this we have already, or we are publishing. This is already accepted for publication in Journal of Applied Crystallography. Okay, so now sufficient for bulk materials. I will go now to another topic, to epilayers. So first of all, I would like to present you some results on heteroepitaxial gallium nitride epilayer on sapphire. So please, let's have a look on the left-hand side first. So here we see only sapphire substrate. So it's a bare sapphire substrate without any epilayer, and we get such a result. Again, yeah, we have a very large wafer, 150 millimeter, I think it was. And then we can zoom in and you can analyze all these defect structures which are in this sapphire substrate. And now you may ask, okay, if I put a gallium nitride layer, are there effects? Yeah, how can I characterize this? And this is possible with the XRTmicron. This you see now on the right-hand side. And what you can see is now, so we have here the sapphire, and on it we have a 3 micrometer thick gallium nitride buffer. We can now measure the substrate below this layer, yeah, if we now choose the reflex of sapphire. And the gallium nitride then only serves as an absorptive material. That's the reason why the signal noise ratio is not so easy. Also, we have some problems with curvature here. The wafer is more curved than the bare substrate. Nevertheless, we are able to make the mapping, and we can identify, for instance, here at this position, large dislocation clusters in the substrate of sapphire. And now, if we go on the reflex, asymmetric reflex in reflection of the GaN buffer, we can now also map this, yeah, and we can zoom at the same position here, yeah, and what you can see that this cluster defect has affected the gallium nitride buffer at this position. Yeah, and of course, this also may affect your devices and so on. So in this sense, we can see at which positions substrate may affect the epilayer. So this is an example for gallium nitride, and now I will go to 4H silicon carbide. So please, first I will a little bit motivate the problem. Here, the green part, you see our silicon carbide substrate. So this 350 micrometer thick wafers typically. And on it, this orange color, you have an epitaxial layer. With the black lines, I symbolize the basal plane, yeah, which is 4 degrees off to the wafer surface, is of course exaggerated, yeah, but just that you see that you have some off angle. And the threading screw dislocations are of course perpendicular to the C-plane, yeah, and typically they go through to the epilayer. This is very well known, but some of them, of this threading screw dislocation, are converted into some killing defects, yeah, for instance, like stacking folds, triangle defects, carrots, and whatsoever. Also, the basal planes, most of them are converted in DEDs, which are considered to be harmless, yeah, but some of them are also converted in killing defects. So this is also, remember on our DSD mappings of 4H silicon carbide motivation, why this is important to have maps of DSDs. Because if you have the maps where you have large densities, you expect also that there is more problem with these killing defects. Okay, so this is now, we can have measured this now, the effect of this epilayer on this 4H silicon carbide. So what you see here are topographs of the 1,1-28 reflex. On the left-hand side, again, you see substrates. Yeah, so these are two topograms of substrates, two different substrates. They have a same defect structures because they are out of the same crystal. And I have chosen now here one where you see a very nasty defect cluster here. Yeah, so you can zoom in, yeah, and look it closer at it for the both substrate. And then we processed an epilayer on it. Yeah, so here we have a 31 micrometer thick epilayer on it, here below a 30 micrometer epilayer on it, and then we measured the substrate with the epilayer in reflection from above. So what you see here now for the thick epilayer, yeah, that if you enlarge this position, that the defects has almost vanished somehow. So if you have a good epilayer process, yeah, you can get rid of a lot of defects from the substrate. Nevertheless, where you have this, let's say, this large part of defect clustering, of course, you see always something. The problem goes really inside the epilayer. But the rest is almost free of it. And again, important is penetration. Yeah, so here we have simulated the penetration and simulated what part of intensity is from the epilayer, what part of the intensity is from the substrate. And it turns out that 13% is from the substrate and about 90% almost is from the epilayer. So here what we see is we are sure that almost everything we see is from the epilayer. A little bit more complicated for thin samples, of course, since we have, let's say, a deeper penetration inside the crystal. We see now here 40% of the substrate. So therefore, the defects we see here is a lot of information of the substrate. So here you need really to compare to see if you have an improvement or not. Of course, you see you have an improvement of the epilayer. Nevertheless, the separation between homoepitaxial layer and substrate becomes for thin samples more complicated. Nevertheless, what we have is three-dimensional reconstruction. This I would like to show you now, because this also may help to identify what defects we have in the epilayer. So first of all, let me shortly repeat what Taka already explained to us, namely how three-dimensional section topography actually works. The idea is very simple. The idea is that the typical source beam, we put a micro slit inside so that we have only a very, very thin X-ray beam here, yeah, which slices out a part which is excited of the wafer here. Yeah, and the detector detects a slice. Yeah, so this is actually what we can measure and what we can see here. And then the idea is clear. What we have to do is just to scan through the wafer. Yeah. And then you have all these slices here, yeah, all these slices, and the rest is actually only with software, yeah, with modeling. You make now a reslicing, yeah, with this image software, and you have now from the front to the back, you can have slice for slice through the wafer. And a result, a typical result you see here on the left-hand side. Again, this is the silicon wafer with some deposited structures on it with these glide planes. And now you see not only, so you see, in the beginning you have seen the integrated information, but here you see now how these glide planes actually evolve through the wafer. Yeah, at which position in the depth actually is the glide planes enters inside this wafer. Similar thing you can do now for 4H silicon carbide, which I would like to show you now. So in the middle, you see now a 3D screw dislocation map of some wafer, as we have seen at the beginning. So we have regions where we are almost free of dislocations. For instance, at these positions, you see here the dislocation density is very low. Yeah, in this snapshot here, it's enlargement of this area. Also here the enlargement now of a very high density part of this wafer. You see also here that this density is more crowded. Yeah, so that the defects are more crowded here. And now what you can do on such an area of interest, you can make a section topography, yeah, which we have done on both sides. And the result you can see here. So let me scan quickly through the wafer. So this is at the top and this is at the bottom. Yeah, at the bottom, at the back side, what you see here are some scratches here, the straight lines. Then you go through the wafer. From the back, you see basal planes, yeah, inside the wafer and other defects. And finally, you are at the surface. Here, you are actually in the epi-layer. Yeah, so this basal planes has already gone. Yeah, and you can now justify where this defect structure change. Even more impressive is this in this high density area. Yeah, if you go now through the wafer, you see, of course, this is more crowded. Yeah, in comparison to above, we have here much more, the density is much more higher. And therefore, we expect killing defects. And this you see here. Now we are at in the epi-layer, and you see these triangles here. Yeah, and these are our killing defects, yeah, our triangle defects inside the epi-layer. Now, and you see, so this is now the surface, and now these triangle defects are there, and now we are in the substrate again. This is now only substrate, yeah, and the rest, of course, is always substrate. No? So therefore, with this method, you can actually see where our defects are. Now, you can, of course, make a three-dimensional modeling. I also would show you to this. So the process would be you make a map first of your wafer, yeah, a transmission scan typically. Then you look at some area of interest to make enlargement until you see something interesting. For instance, this triangle defect, and you say, okay, this I want to see better. Then you make here a section topography, and this is what you see here below. You can now make flow through the wafer, yeah, make slice by slice to see how this triangle defect actually looks like, and you can make a three-dimensional modeling, yeah, of this triangle defect, and you can then, let's say, study this if you like. Okay, so now I will stop my talk with a summary. So please have in mind, remember that this is a non-destructive structure characterization tool. You do not need to make etching, yeah, in order to count your defects. You have high quality. Yeah, it's really of high quality. I hope I have persuaded you of this. And you can really make a quantitative defect characterization, yeah, of the complete wafers. The measurement is quick. You can make a large throughput. Please remember in Taka's talk, the loader. Yeah, there you can load wafer by wafer full automatically and make your measurements. And of course, since it's in your lab, you have very short feedback time. You have 100% accessibility at moderate costs. And the wafer geometry, you have a wide range of wafer geometry from 300 millimeter. This is the largest one. And you can measure in transmission, reflection, and make a three-dimensional reconstruction. So all kind of crystals you may measure. For instance, here you have seen silicon carbide and nitrides. Of course, also any other wafers. And I hope I have persuaded you that this is really a good tool for quality control in production and research and development, for instance, for wafer suppliers and also for device suppliers. Okay, so thank you very much for your kind attention.